So what I want to do now is go over a number of different examples, just kind of illustrating how to apply this second derivative test to classify maximum and minimum. And to do that, what I'll do is use some of the examples that we went over in the last lecture on solving for critical points, because these examples should be relatively familiar to you. So we'll take the function 3y squared minus 2y cubed minus 3x squared plus 6 times x times y, and try to classify these critical points and verify some of the results that we got the other day. And to this end, you'll remember from the previous lecture that first step was to solve for the partial derivatives. In this case, the x partial derivative of this expression is going to be negative 6 times x plus 6 times y. The x partial derivative of this and the x partial derivative of this. X partial derivative of both of these terms is 0 because the only function here, or only variable here, is y. Likewise, the y partial derivative of this expression is going to be 6 times y minus 6 times y squared plus 6 times x. And you'll recall from the previous lecture, the method shown in the previous lecture, that in order to solve for the critical points, we have to solve for all points where df dx and df dy are simultaneously 0. When we did this in the last lecture, we found that there are two critical points, specifically critical point 0, 0, and the critical point 2, 2. So x equals 0, y equals 0, and x equals 2, y equals 2. So for classification using the second derivative test, we need the values of the second derivatives and the discriminant of this function. Second derivative of f with respect to x is going to be equal to, well, you can also term this as xx for simplicity. This will be negative 6 because it's the x partial derivative of the x partial derivative of f. So it's the x partial derivative of this. The y partial derivative of f with respect to x. Second y partial derivative is going to be f sub y, which is the y partial derivative of this function right here, which will be 6 minus 12y. And then for the mixed second partial derivatives, we actually have that Clairaut's theorem holds. So fxy is equal to fyx. And this is going to be exactly either the y partial derivative of this function or the x partial derivative of this function, which in either case is just equal to the value of 6. So for the discriminant, we can directly go through and evaluate these at both critical points, but sometimes if the function is simple enough, you can actually just get the discriminant as a function of x and y. This is fxx times fyy minus fxy squared, which is going to be equal to negative 6 times 6 minus 12y minus 6 squared, which simplifies after a little bit of algebra to just 72 times y minus 1. So to do our second derivative test, we create a table. This table is going to contain the critical points in the first column, and the value of the derivatives and the discriminant, the second partial derivatives and the discriminant, in subsequent columns. And then in the last column, we'll be able to determine the classification. This is fxx, column for fyy, column for fxy, and then lastly column for d, which is sometimes noted as delta, which is fxx times fyy minus fxy squared. And so this is fxx at 0, 0 is negative 6, and also at 2, 2 it's negative 6, stays constant. fyy at 0, 0 is going to be 6 minus 12 times 0, which is 6, and fyy at 2, 2 is going to be 6 minus 2 times 12, which is 6 minus 24, or negative 18. fxy at 0, 0 is just going to be 6, and same thing with fxy at 2, 2, because this is a constant function. And lastly, the discriminant, when we plug in 0, 0 into the discriminant formula, we get 72 times 0 minus 1, so it'll be negative 72. And likewise, when you plug in the value 2, 2 into this formula, you're going to get 72 times 2 minus 1, which is 72 times 1, or 72. And so for our classification test, we look at this column and at this column. And we conclude that because the discriminant is negative at 0, 0, this must classify and be a saddle point. And it's positive, the discriminant's positive at 2, 2, but the first second partial with respect to f, with respect to x of the function f, the second partial derivative of f with respect to x at 2, 2 is negative, so this classifies as a local max. And this is exactly what we saw when we plotted out the function and looked at the level curves, gradient field, and graph of the function in the previous lecture. So I'm going to pull that up right now just so we can kind of really bring this home. So here I've plotted a contour plot of our function, and you can very clearly see that at 0, 0 we have a saddle point here, and at 2, 2 we have a local maximum, which is exactly what we predicted using the second derivative test for our critical points. And if we rotate this a little bit, we can see a little bit more why this is holding at each one of these points. See that there are regions around 0, 0 for which, as we move away in a given direction, the function decreases, and if we move away in this direction or in this direction, the function increases. So this is why the second derivative test is showing that this is a saddle point. And this point right here, we see that no matter what direction we move, the function is going to be of a lower value than the value of the function at this point. So it's a local maximum, and we can very clearly see that the second derivative test is giving us the correct result. So in the previous lecture, we talked about the function of two variables, x times y times e to the negative x squared plus y squared. And we went through and we showed through a sequence of computations that this function has 5 critical points. And these 5 critical points are located at 0, 0, L, L, negative L, L, negative L, negative L, and positive L, or positive L, negative L. Where L here, I'm just kind of simplifying, L is 1 over the square root of 2. So in order to apply the second derivative test, we need that. And we also need to remember what we did and how we calculated the the second derivatives of the function, specifically that when you go through and get the second x derivative of this function, you end up getting that this is the same thing as 2xy times 2x squared minus 3 times e to the negative x squared plus y squared. For fyy, you have something very similar. You get 2xy times 2y squared minus 3 times e to the negative x squared plus y squared. And for fxy, when you get the mixed partial derivative, you get that that's equal to 1 minus 2x squared for the mixed second partial derivative. 1 minus 2x squared times 1 minus 2y squared times e to the negative x squared plus y squared. So remember, when we solve for those 5 critical points, that's the same thing as solving for when the gradient is equal to 0, the 0 vector, or when the x partial derivative is equal to 0 and the y partial derivative of the function is also equal to 0. That's the equation we had to solve for those 5 critical points. A system of 2 equations. But with this information now, we can actually go through and do out the second derivative test for these 5 critical points without even plotting out the function. Now, if you remember the plot, and you go back to the plot, you'll see that the second derivative test, when we do this, exactly verifies the result that we got when we plotted out this result. The main thing that we're going to kind of rely on here is the fact that, well, when you plug into these expressions at, say, we'll just do 2 of the points to show you what you're going to end up getting and how to plug in. At 0, 0, fxx of 0, 0 is just going to be equal to 0, because when you plug in 0 here for x and for y, this expression is 0. You get the same thing when you plug in 0, 0 to fyy. Then when you plug in 0, 0 to fxy, you're going to get 1 times e to the 0, which is equal to 1. So this tells us that the point 0, 0 is a saddle point. Why is this? Well, it's because the discriminant is equal to 0 times 0 minus 1 squared, or negative 1. Because that's less than 0, this point will classify as a saddle point. Doing this process again for the point L comma L will give you that fxx at L comma L, and you plug in there, you'll get 2 times 1 over the square root of 2 times 1 over the square root of 2 times 2 1 over the square root of 2 squared minus 3 times e to the negative 1 over the square root of 2 squared, which is 1/2 plus 1/2, which ultimately simplifies to just being equal to negative 2 times e to the negative 1. So fxx is negative 2 times e to the negative 1. When you plug in for fyy, you get a similar, same value actually. And when you plug into on this should be fxy here, just to kind of keep consistent. You plug into fxy at L comma L. Look at that, this is equal to 1 minus 2 times 1 over root 2 squared, which is 1/2, times 1 minus 2 times 1/2 times e to the negative 1, which is equal to 0. So the discriminant for this critical point is going to be this value, fxx times fyy, which is 4 times e to the negative 2 minus 0, which is positive. So because fxx is negative and the discriminant is positive, this point, the point L comma L, is a local max, which directly matches up with the plot of this function from the previous lecture. Now, to kind of keep track of all this, a lot of times if you have multiple critical points, you want to make a table and just write down these computations in the table itself. So you make a column in the table for the critical points. A column in the table for the second partial derivative with respect to x. I'll let you go through and you should verify these computations, but essentially this is going to be 0. We just calculated that this is going to be negative 2 e to the negative 1. At negative L comma L, you get this is going to be 2 times e to the negative 1. Negative L comma negative L, you get negative 2 e to the negative 1. And at L comma negative L, you get 2 times e to the negative 1. For fyy, you get 0, negative 2 e to the negative 1, 2 e to the negative 1, negative 2 e to the negative 1, and positive 2 e to the negative 1. Of fxy, we calculated this is 1. And then all of these are actually going to be 0 when you plug in these points into fxy. And then lastly, you have a column for d, which is the discriminant, or fxx times fyy minus fxy squared. We showed that this ends up being equal to negative 1 for this point, and then it'll alternate in the following way. You multiply these two together, you get 4 times e to the negative 2. Multiply these two together, you also get 4 e to the negative 2. It'll be the same for all the other points as well. So to apply the second derivative tests kind of en masse, or to every one of these critical points, what you have to do is look at the sign of this column right here and the sign of the discriminant column, the sign of the values in this column right here. And from our second derivative test, the discriminant is negative here, so this is a saddle point. It's negative here and positive here, so this is a local max. It's positive here and positive here, so this is a local min. It's negative here and positive here, so this is a local max. And lastly, it's positive here and positive here, so this is a local min. But this is exactly how you would do the second derivative test and apply it to this example. So this is a very, very important procedure because it essentially tells us the correct way of classifying multivariable critical points using the second derivatives, the second partial derivatives of a given function. So just to provide a graphical clarification and verification of this result, we can clearly see here in the contour plot of this function, we plot the contours and the density of this function at every point. What we've just done is completely verified, because here at L, or the point LL and the point negative L, we have a local maximum of our function. Here at the point negative LL and L negative L, we have local minimum. And here we very clearly have a saddle point of our function. Sure enough, if we rotate this plot a little bit to see this better in 3D, again, we can very clearly see what these 5 critical points classify as by looking at this plot. And we see that what we've done on paper, which is classify the critical points, was done correctly. So the results of the second derivative test are very clearly being verified by this example. So for the last example that I want to consider, this is going to be the function f of xy is equal to x cubed minus 3 times x times y squared. And the graph of this function is sometimes called the monkey saddle. And this will become very, very apparent once we see this and kind of try to interpret this. This is a kind of a fun example. But this is a good example of when our second derivative test is actually inconclusive, and nevertheless it's still possible to classify the critical point as some kind of saddle point. So the x partial derivative and the y partial derivatives are the first thing that we need to solve for the critical points. The x partial derivative of this is going to be 3x squared minus 3 times y squared. And the y partial derivative of this function is going to be negative 6 times x times y. And when we're solving for the critical points, we're looking specifically at solving for a simultaneous solution of the first derivative being equal to 0 and the second derivative being equal to 0. So equation 1 and equation 2 here. Now, the simpler of these two equations is equation 2. Now, equation 2 is satisfied if either x equals 0 or y equals 0. Those are the only two solutions of equation 2. Because negative 6 is non-zero, which means the only way of satisfying this equation right here is having x be 0 or y be 0, which means that if x equals 0, in the first case here, we have the equation negative 3y squared is equal to 0. This is equation 1. Or, if y is equal to 0, then we get the equation for equation 1 that 3 times x squared is equal to 0. And in either case, right, this is only satisfied when y equals 0, and same thing here, this is only satisfied when x equals 0. And therefore, we have that there's only one critical point to this function. That one critical point is exactly the origin, x equals 0, y equals 0. And if we go through to classify this critical point, and if we go through and take our derivatives to do our classification test, we have that fxx, the x partial derivative of this, is going to be 6 times x. Fyy is going to be the y partial derivative of this fy right here, which is going to also be negative 6 times x. And fxy, the same thing as fyx, and this will be equal to, well, if we take the y partial derivative of this, we get negative 6 times y. And if we take the x partial derivative of this, we get negative 6 times y as well. This will be negative 6 times y. And so this means our discriminant is going to end up being 6x times negative 6x minus negative 6y squared, which will be 36 times negative 1 times x squared, and then minus 36 times y squared, or negative 36 times x squared plus y squared. And what this means then is that at the critical point, at 0, 0, fxx at 0, 0 is equal to 0. Fyy at 0, 0 is also equal to 0, f xy at 0, 0 is equal to 0. And lastly, d, the discriminant, is equal to 0. So this point falls under a critical point of type 4, where our second derivative test is inconclusive. And the idea here is that this doesn't mean that we can't classify the critical point. It just means that the second derivative test that we've stated is not strong enough to do it for this function. So you have to look into other methods of classifying the critical point, of which there are several. But I'm just going to show you a plot that I've produced using Python to justify this and show kind of an explanation here. This is actually what's called a degenerate critical point, because all of these are 0. So let's open up the Python plot and take a look at what we get. So this is a density contour plot of our function, and you can very clearly see that right at that point 0, 0, we definitely have some type of saddle point, because there are regions where as we move away the function increases, and there are regions where as we move away the function decreases as well. This is why this is a saddle point. It's a type of saddle, but it's not like any saddle we've ever seen, because there are actually now 3 regions in which the function decreases and 3 regions in which the function increases as we move away from that critical point. So let's rotate our view a little bit and get an idea of what this looks like in 3D. We very clearly see that all of those partial derivatives should be equal to 0, right, at that point, because the function is very, very, very flat at that point, the critical point. And if I kind of zoom out a little bit so that you can see the contour plot of the function underneath the actual function, so you can see kind of a picture from before. This shows the graph of the function right here. And it becomes very, very clear why this is called the monkey saddle shape. Right? This is called the monkey saddle surface because monkey has a tail as well as 2 legs. So in order for a monkey to sit comfortably on a saddle, you need 2 spots for his legs and 1 spot for his tail. And this is a very, very good example, right, of a degenerate critical point, or a critical point where the second derivative test is inconclusive. So I'm going to end the lecture right here. I hope you had a fantastic day, and I hope you learned something, and I look forward to seeing you in the next lecture.